good evening to one and all present here. So let us carry forward with our discussion on special concretes. Okay. So we shall be entering the 6 weeks course contents. Okay. Here we shall basically go through one of the important parameters of concrete, which is basically the rheology, and which we shall go in a brief manner about what is rheology and how it affects. Okay. How it helps in classifying the concrete, and then we shall go to another type of special concrete which is known as fiber reinforced concrete. Okay, so let us begin our discussion today. So rheology, as I said you, rheology is one of the important parameters for concrete, and it is basically associated with the study of flow behavior. Okay, and it is applied to fluid materials or materials that exhibit a time dependent response to stress. Okay, so uh, the fresh concrete, okay, as we know, is a fluid material whose rheological behavior affects or limits the way it can be processed or placed. Okay, so for finding out its fresh concrete parameters in a more detailed manner, so its rheological behavior is utmost significance. Slump is a rheological measurement, for example, but it does not describe the entire rheological behavior. Okay, so it is just one partial, one of the partial characteristics and understanding we get through the measurement of slump about fresh concrete. Okay, and this one, the flow behavior of concentrated suspensions can help us measure and understand the behavior of fresh concrete. Okay, so all we have to study various aspects such as suspensions and various other parameters such as strain and all to find out the behavior of flow. Okay, as you can see in this picture. So how to measure the flow? Flow is typically measured using shear parameters of stress and strain rate, which are normally obtained from the direct measurements of torque and flow rate in rheometers. Okay, so the for understanding the behavior or to study the flow behavior or to study the rheology, the instrument we use is rheometer. Okay? So it gives us various parameters, shear parameters such as stress and strain rate. Okay, so stress can be found out using the torque and strain rate. Okay, so it can be obtained from viscosity and various other parameters. Okay, so viscosity is the representative parameter used to assess the flow behavior and is defined as the ratio of stress to strain rate. Okay, so we have to see this is not strain but strain rate. Okay, so this is viscosity, unlike elastic modulus, which gives us the ratio of stress to strain in solids. Here the viscosity gives the ratio of stress to strain rate. Okay, so as we found in the last class, okay, so we studied about self-compacting concrete. There we found that for SCC we need both high deformability and high segregation resistance, right? So for high deformability we use super plasticizer, okay, and for high segregation resistance we use reduced water powder ratio. So for both, using both we can obtain the concept of SCC. Okay, and for that we need limited amount of aggregate volume. Okay, so that this is very important parameter. So experiments have been done basically using some mortars. Okay, so here the results are shown for various mortar tests carried out varying the sand content and hole diameter. Okay, and it has been observed that there is a sudden tendency for blocking to occur, as you can see. So as you can see here, after the sand volume increases from say 42%, there is a possibility of blocking which becomes 100% after it reaches 44%. Okay, in case of mortar. And as you can see here, critical volume for sand of sand for blocking. So as the ratio of hole diameter to average size increases, okay, then also the chances of blocking occurs, okay, increases. So as it goes on increasing, the ratio of hole diameter to average size of sand, the critical volume of sand also increases. Volume of sand for blocking also increases. So more is the hole diameter, so better is the this one, lesser is the chance of critical blocking. Okay, so greater is the chance of sand blocking because the critical volume also increases. So coarse aggregate in concrete, it is simulated by the large sand particles in this case, as you can see, and the concept can be therefore extended to concrete. Okay, so we need to study blocking tendency, especially near the bars, because there the hole diameter is very much low because of lack of space, right? So you know, for also we can find like also there are a few important terms such as water retention. Okay, so that is obtained using a mini slum cone for mortar. Okay, so the relative flow area, that is basically equal to final area minus initial area by initial area. Okay, so using this equation, okay, a concept of zero relative area is obtained. Okay, so in a concept of zero relative area, the final area and the initial area is the same. Okay, that means in the case of zero relative area for mortar or paste, there is no deformation at the base. Okay, so because the final area and initial area is the same, no deformation takes place at the base. Okay, and at this condition, the water content is defined as the water retention in mortar paste, because there is no deformation, right? So the flow till where there is no deformation, so there the water maximum water content possible is called as the water retention. Okay, so they have coined various parameters based on this relative flow area and volume of water and paste, right? So the flow behavior of suspension. Okay, so suspension, as we might have discussed, is basically solid particles, okay, which are dispersed or flocculated in liquids. Okay, so they can be either in the can be either scattered, dispersed, or combined or aggregated in flocculated manner in case of liquids. Okay, where solid particles are present in a dispersed or flocculated manner. So the key factors affecting the flow behavior of suspension are basically two. Okay, so one is the volume of solid particles, which is termed as Vs, and the second is degree of agglomeration or flocculation, right? So Vs, that is the solid particle volume, its increase causes the increase in viscosity. Okay, so that's why it is an important factor. And in the case of degree of agglomeration or flocculation, a result of that is mainly caused by a result of interparticle forces. Okay, so other influencing factors of flow behavior are temperature and pressure. Okay, liquids with higher viscosities, okay, generally have greater temperature sensitivity. Okay, and viscosity increases with the increase in pressure, though the changes are minimal at atmospheric pressure. Okay, now what are the various types of flow behavior which can be observed? Okay, so basically four types of flow behavior has been observed. Okay, one is Newtonian, one is Bingham plastic, so both are linear. The Newtonian does not have any initial stress. Okay, so it starts from zero, that is origin, whereas the Bingham plastic has some kind of its initial stress present, so it starts from some value tau naught. Okay, in the case of shear thinning, that is pseudoplastic, what happens is with the increase in strain rate, the increase in stress decreases. Okay, so that's why the capacity decreases. Okay, and it becomes plastic in nature. Okay, whereas in the case of shear thickening, okay, so in the case of shear thickening, as with the increase of strain rate, okay, there is the amount of stress required also increases. Okay, so that's why it thickens. Okay, so more capacity is required, achieved. Okay, so for basic constitutive relations for plastic behavior, these four types of stress strain rate behavior is obtained for flow. The Bingham model can be modeled as tau equal to tau naught plus eta p gamma dot. Okay, and for pseudoplastic power law model, that is shear thinning, tau is equal to gamma dot k gamma dot to the power n, where tau naught is the yield stress, initial yield stress, k is the consistency, n is the power index, eta p is the plastic viscosity, and gamma dot is the rate of shear strain. Okay, so so as we discussed, so suspensions are of two types. One is flocculated and one is dispersed, right? So what, let us now understand in detail what are flocculated suspensions. So flocculation of colloidal particles, right, which are scattered basically. So particles smaller than 1 micron in diameter, right? they could result in aggregation or formation. Okay, so flocculation, which is basically agglomeration. Okay, so particles smaller than 1 micron in diameter, they could result in aggregation or gel formation. The internal forces are fairly weak. Okay, stress at which a breakdown of flocculated network occurs is called the yield stress, right? In the case of dispersed suspensions, they usually show Newtonian behavior, okay, at low solid concentrations. So they basically are, they start from zero. Okay, tau naught equal to zero, as you can see here written. So usually show Newtonian behavior at low solid concentrations. At high solid concentrations, they show considerable yield stress and exhibit plastic behavior, okay, due to crowding of the particles. Okay, so that is why they maybe that is why follow the shear thickening concept. Okay, as the solid concentration increase, okay, due to crowding of the particles. So now let us see how the flow behavior of cement paste is assessed. Okay, so the assessment of flow behavior is normally done using shear rheometers. Okay, so these are instruments which operate in rotation and measure the torque and rotational speed. Okay, fundamental types of rheometers are there, although there are many, as we will see later. So primarily two are there, which are the coaxial cylinders and the parallel plates. Okay, sample sits between and one of the cylinders or plates rotates. Rheometers either control the stress and measure strain rate, or control the strain rate and measure stress. So these are the some of the basic fundamental types of flow rheometer. So this is the example of coaxial cylinder. This is the example of parallel plates. Okay, so this is a torque measuring device. Okay, so in the case of in the case of flow behavior, some common issues are developed, okay, while studying the flow behavior. So they are basically segregation of cement paste. Okay, so this is more likely in a plastic or pseudoplastic suspension at higher strain rates, okay, due to low amount of viscosity. Okay, so due to low viscosity, it is more likely in a plastic or pseudoplastic suspension at a higher strain rates. The segregation will occur, and segregation is less likely in flocculated suspensions and at very high concentrations. So if there is high concentration and there is flocculated suspension, okay, so there is less likelihood of segregation occurring. Okay, so this is a torque measuring device. As you can see, this is the coaxial cylinder and this is the parallel plate. Okay, so the cement paste follows a combination of Bingham and pseudoplastic behavior. Okay, and this is known as Herschel-Bulkley model. Okay, that has been found as per some people who had investigated Papo, Zerbino, etc. So they have found the equation based on that to be tau equal to tau naught plus k gamma dot to the power n for the cement paste flow. Okay, so when dispersed using a superplasticizer, cement paste shows Newtonian behavior at low concentrations and plastic behavior at high concentrations. So that is what we studied in the last, okay, in the last slide here. So here basically, so in dispersed form, they exhibit Newtonian behavior at low concentration and plastic behavior at high concentration, and it has been found based on experiments by Strubble. Okay, so while assessing the flow behavior, there could be some hysteresis in the stress when strain rate is increased from 0 to higher values and brought to 0 after reaching the peak. Okay, so some hysteresis may also be found, okay, in the stress when strain rate is increased from 0 to some higher value and brought to again 0 after the reaching of peak. Okay, so this reflects the lack of equilibrium, okay, between the microstructure and strain rate, and denotes that the material is undergoing irreversible structural breakdown due to shear. Okay, so because of this hysteresis behavior, okay, so that will mean that it is not coming to its original shape, and that means some irreversible structural breakdown might have occurred because of the presence of shear. Okay, basically, so that is the reason why the hysteresis has been occurring. So the concrete exhibits plastic behavior, that is the typical flow curve of concrete is shown here. Okay, so in In concrete, uh, the particles cover a broad range, okay, from micron size cement to centimeter size aggregates. Okay, the flow, we all know concrete has a varied range, okay, from micron size cement to centimeter size aggregate. The flow depends on the concentration of particles and the extent of flocculation of the cement particles, right? So flocculation is only important for the finer particles. Okay, range of strain rates during testing should be low to simulate the actual conditions, field conditions. Okay, which may be occurring in mixing, transporting, placement, and finishing. Okay, so these are some of the conditions to be noted. So flow behavior must be described using the yield stress and the plastic viscosity due to the Bingham nature, right? Coarser particles tend to settle due to gravity, and segregation is more likely to happen during shear. Okay, so these factors will occur. Okay, we have to keep in mind. Slip near the wall of rheometer could be aggravated due to larger gap, which is necessary because of coarser particles. So these factors need to be kept in mind. So now let us see the effect of composition on flow behavior of concrete. So water cement ratio, if it is increased, it results in lower yield stress and plastic viscosity, which is obvious. The total aggregate content TAC, the increase in TAC results in an increased plastic viscosity. This is also very much trivial. Aggregate type concrete with river gravel, okay, due to its much rounded and smoother surface, it has lower viscosity and yield stress. Okay, because of its rounded and smoother surface, there is lack of interlocking, so that results in lower viscosity and yield stress, right? And sand content, both yield stress and plastic viscosity follow an initially decreasing, followed by an increasing trend with the increase in sand content. So this has to be kept in mind. The lowest yield stress and plastic viscosity occurs for a sand content of 38%, okay, as per Strubble. So the lowest yield stress and plastic viscosity has been found at a sand content of 38%. Okay, now in the case of admixture, replacement of fly ash, okay, reduces both the yield stress and plastic viscosity. Okay, so this is the uh, this can be benefit also in some case as well as drawback also. Okay, so it reduces both the yield stress and plastic viscosity. In case of superplasticizer SP, addition of SP reduces the yield value of concrete and plastic viscosity. Similar, okay, admixture, fly ash, and superplasticizer, they reduce the yield value and plastic viscosity. Whether the addition of superplasticizer is with water or later could also have an effect on the results. So that needs to be researched. Okay, and elapsed time. This is obvious. Both yield stress and plastic viscosity, they will increase with the elapsed time after mixing. So after more the time after mixing, more the time elapsed after mixing. So higher will be the yield stress and plastic viscosity. Okay. Now shear induced flow in fluids. Okay, so in the case of shear induced flow, four laminar flow model cases occur. Laminar flow, as we all know, is the flow in layers, and where the flow is in a straight line, a smooth and straight line in layers. Okay, so in that case, in case of shear induced flow, four laminar flow model cases will occur. One is the flow between two parallel plates with linear motion. Second is the flow in the annular gap between two concentric cylinders. Third is the flow between two parallel flat plates with rotation. And fourth is the flow through pipes and tubes. Okay, so these four laminar flow model cases occur in shear induced flow. Okay, in case of fluids, the above models can be used to study the relation between shear stress and shear rate. Okay, so these models can be used for studying the relationship between shear stress and shear rate. Okay, in analyzing the flow behavior, the following are the basic requirements. Okay, so it must be homogeneous, that is, sample must react to shear uniformly throughout. In case of suspensions, all ingredients should be very small with respect to the thickness of the sample. For ensuring the measurement in suspensions, the shear gap is normally kept very low. The composition and particle size distribution of the sample dictates the shear gap, right? In case that is the all about homogeneity. Okay, so basically first has to be homogeneous, second it has to be laminar, that is it should travel in a smooth line, straight line, and in layers. So exchange of volume between the layers should always be prevented. Okay, no slippage between the sample and the plate will be allowed. Okay, should be allowed. And the rheometer basically applies or measures these two. Okay, so it will either apply torque or force and measure the angular displacement or angular velocity, that is the strain rate, okay, and viscosity, or it will measure the apply the angular displacement or angular velocity and measure the torque or force. Okay, so one has to be found using the other. Okay, in the case of simple steady shear flow, okay, the top plate area is equal to A, okay, and the bottom plate is stationary. Okay, so as you can see, if it flows in a straight line, this is laminar. Okay, the force applied is F. Okay, the shear stress in Pascal is equal to F by A. Strain rate is equal to X by Y, where X is a function of time. Okay, shear strain rate, that is second inverse, is equal to shear strain by time, and viscosity, that is in Pascal seconds, is equal to shear stress by shear strain rate. Okay, so using these parameters, we can define the simple steady shear flow. Okay, so viscosity is basically shear stress by shear strain rate. So now let us see the torsion flow in parallel plates case. Okay, so here the shear stress due to torsion is equal to 2 pi r cube, 2 by pi r cube into m is equal to k sigma into m. The shear strain is equal to r by h into theta, which is equal to k gamma into theta. The shear strain rate, that in second inverse, is basically r by h into omega. So basically r is the radius, as you can see, of the plate. H is basically the distance between the plates or thickness of sample. Omega is the angular velocity, right? So viscosity is equal to shear stress by shear strain rate, as we discussed just now. And m is torsion, omega angular velocity, h distance between plates, r radius of plate, k sigma and k gamma are the constants of stress and strain respectively. Okay, so uh, in the case of parallel plate rheometer, basically where the torsion has been applied, okay, torsion flow is possible. So here you can see the stationary base having diameter d. So the stationary plate is just above that, and above that is the sample, which is closed by the rotating plate. So the above plate rotates and the down plate is stationary. Okay, so the higher thickness of the sample is h, and that is basically the gap between the plates. So this is the case of parallel plate rheometer. So this is ideally, parallel plate rheometers are suitable for materials that may slip, okay, or very low viscous fluids. Okay, it can travel fast, and samples with large particles. Okay, so it will not have that much problem. So strain constant k gamma is equal to r by h, stress constant k sigma is equal to 2 pi r cube. Okay, in the case of coaxial rheometer, so that is basically there are two cylinders, sorry, which is having coaxes, which are coaxial. So the axis is same. So this is the outer cylinder having a radius of r naught. This is the test sample, okay, and this is the inner cylinder having a radius of ri, okay, and this is the length L of the cylinder, and this is omega, right? So this is a stationary base. Okay, so in control strain conditions, torque is measured on the rotor axis, okay, and outer cylinder remains fixed. Okay, strain constant is a function of r naught and ri. Okay, stress constant is a function of r naught, ri, and L. Okay, so stress takes into account the L, length of cylinder, whereas strain is only r naught and ri. Okay, so this is the concept. Okay, different rheometers for testing fresh concrete and mortar. So they can be coaxial cylinder type Tattersall apparatus, BML viscometer, BTR HEOM rheometer. So these are some of the types of rheometers which are used generally for fresh concrete testing and mortar testing. So we shall go very briefly about them in the coming slides. So coaxial cylinder type, as we know, This is principle in principle is similar to that described in the flow of paste. The tendency of segregation, slip and plug flow are the issues, especially in low viscous concretes. Typically the gap between the inner and outer cylinder, okay, in a coaxial cylinder rheometer must be large, okay, compared to the maximum particle size, okay, then only the particle can flow, and it must be small compared to the diameter of the inner cylinder, okay, so that there is no issue of no issue of deformation, okay, deformation of the machine, okay. And this one, uh, if this due to the if it is small, then there might be the deformation due to the amount of flow, okay. So if these requirements are to be satisfied, the dimensions of the rheometer for concrete would become huge, which is highly impractical. So this is one of its anomalies or drawbacks, okay. So next, let us come to the tetrarsal apparatus. So this is designed to reduce the tendency of segregation. As you can see, the helical impeller has a vertical axis and rotates in a cylindrical container of fresh concrete having the same axis. Blades reduce the segregation, okay. Torque tau exerted on the helical impeller and its angular velocity omega are measured. Stress and strain rate are not directly measured, okay. From the flow curve, two parameters are obtained by linear regression: G, which is in Newton into meter, and H, which is in Newton into meter into second, which are analogous to yield value and viscosity respectively. So the equation comes to be tau equal to G plus H omega, okay. In the case of BML viscometer, this is coaxial type with vanes on inner and outer cylinder, right? The equipment measures the torque tau produced on the stationary inner cylinder while the outer cylinder is rotating at various speeds omega. Ribs eliminate the slip between inner cylinder and concrete. Changing the measuring speed and the measuring torque are fully computerized and automated. By comparing the torque at a given speed in the first registration sequence and the torque at the same speed but in another registration sequence, the computer assesses whether the concrete is prone to segregation. So basically, if if the speed and if the torque, if the speed is constant, the torque should also be constant, right? But after changing the registration sequence, if the torque gets changed for the same speed, that means, or mainly if it has become low, okay, so that means segregation has occurred in concrete. So using that, we can check that also, okay, that whether the concrete is prone to segregation. That is the use of BML viscometer. And lastly, let us go what is this one, BTR-HEOM viscometer. So it is basically a rotational rheometer that utilizes a parallel plate geometry. Okay, both the plates are vaned, slip and plug flow are controlled. The horizontal shear in the fresh concrete offsets the effect of segregation, right, by gravity. So the horizontal shear which is happening in the fresh concrete, that will offset the segregation effect which is occurring because of gravity. It is small enough to be easily transported, okay, to a construction site. Torque and angular velocity are measured at different loadings, right? And the fundamental rheological shear, yield stress, and plastic viscosity, these two fundamental properties, right? The fundamental rheological properties, shear, yield stress, and plastic viscosity, are obtained from the following equations, right? So one equation is tau naught is equal to 3 tau naught by 2 pi into rho naught cube minus ri cube, and second eta p is equal to 2h into del t by del omega by pi into rho naught to the power 4 minus ri to the power 4, right? So using these equations, we can find the yield stress and plastic viscosity, okay. And so that is basically all about the equipments, okay. So using all the concepts of angular velocity and torque, we can find the rheological parameters, which is basically the shear stress and the shear strain rate or the viscosity, right? Using the shear yield stress and plastic viscosity and various other parameters, we can mainly find the two parameters which are the important ones for categorizing our understanding our behavior of flow, right? So these are the two rheological parameters, okay, which we have to take into account. right? Okay, then with this we shall we have briefly gone through the rheology. Okay, so this much is sufficient for our purpose. For more, you can go through various books and literatures and find out in depth detail about these techniques. Okay, so now let us go to one special fiber reinforced concrete, which is one special type of special concrete, which is the fiber reinforced concrete. So development of fiber reinforced concrete, or FRC as it is termed, its connotation. So it's it attempts to address the following attempts to this is FRC is the acronym of fiber reinforced concrete. So it attempts to address the following two deficiencies of cement based composites. One is a relatively low tensile strength, and second is low energy consumption capacity, which is also called as toughness. Okay, so this typically uses fibers in cement based composites for shrinkage, crack control, mechanical property enhancement, improving flexural performance, impact resistance, and to already failure mode, right? So the matrix concrete and fibers, in the case of matrix concrete, here you can see two types of fibers can be used. One is continuous fibers, which are straight lines, and one is discrete short fibers, which are in random directions, right? So if you see fiber reinforcement and conventional reinforcement, if you compare basically, so fibers are generally distributed through concrete, whereas reinforcing bars or wires are placed only in predetermined locations. Okay, fibers are relatively short, discrete, closely spaced, and randomly distributed throughout the matrix. Okay, presence of fibers in concrete modifies the properties of concrete per se or per requirement. This is quite in contrast to reinforced concrete RC. Okay, obviously it is possible to have fiber reinforced concrete used as a part of conventional reinforced concrete. Okay, so these are the advantages of fiber reinforcement over conventional reinforcement, right? So the main factors, okay, the main factors that control the performance of the composite material. Okay, so the main factors which which control the performance of the composite material are basically the physical properties of fibers and the matrix, and secondly the strength, that is a bond strength between fibers and matrix. So these two properties, physical properties and bond strength, so these are the main factors which control the performance of composite material. Okay, and for this we have developed a we develop a term called fiber volume ratio. Okay, so this ratio of fiber volume, it is sorry, the fiber volume ratio, this is basically the ratio between fiber volume and the total volume of FRC. Okay, at a low fiber volume, the addition of fibers contribute mainly to the toughness. Okay, and at a high VF, which is an acronym for fiber volume, so at higher VF, uh, the tensile strength of matrix can be enhanced and the failure mode can be changed. Okay, accordingly. So these are the ways of using fiber reinforced concrete and its various applications. So the properties of the matrix influence the bond, okay, with the fibers and the mechanical properties of FRC. Okay, so FRC can be modified using mineral admixtures such as fly ash, slag, silica fume, metakaolin, etc. So FRC can be further be modified. Okay, so it again increases its applicability. Okay, so if we classify FRC based on fiber volume, there are three types of fiber composites: low fiber composite, moderate fiber composite, and high performance fiber reinforced concrete. Sorry. So low fiber composite, so volume of fraction of fiber is less than 1%. It is used to reduce shrinkage cracking. Okay, in the case of moderate fiber composite, the volume fraction is between 1 and 2%. So it exhibits improved mechanical properties, and it can be used as secondary reinforcement. Okay, and in the case of high performance fiber reinforced concrete, so the volume fraction of fiber is higher than 2%. Okay, so it is used for improved mechanical performance, and it exhibits strain hardening behavior due to high fiber content, which is basically more than 5%. Okay, so these are some of the uses. Okay, so reinforcement of concrete by discrete short fibers. So as you can see, these are the aggregates. Okay, these are the voids. Okay, and these black lines are the fibers. So if you see this void, for example, so this void is surrounded by these fibers, which does not allow the void or say the micro cracks, okay, to serve as crack initiator. Okay, so these fibers prevent the crack elongation and increase of crack width. Okay, so that is the use of these fibers, and that resulted in increase in strength by the fiber spacing theory. Okay, which has been also investigated by Romaldi. Okay, using short fibers in concrete, a fiber length of at least 1.5 times the maximum size of aggregate can be used, considering the use of ease of fiber dispersion. Okay, while a fiber length of 30 millimeter or more is generally recommended, right? So fibers of about 60 mm with a high reinforcing effect are used for slabs. Okay, so all those are criteria how short fibers can be used. So what are the types of fibers? Okay, so fibers can be made from steel, plastic, glass, natural materials such as wood, cellulose, etc. They are available in a variety of shapes, sizes, and thicknesses. They may be round, flat, crimped, okay, and deformed. Okay, the steel, glass, synthetic, and natural fibers with different lengths and shapes have been shown here in this figure. Okay, so they may be round, flat, cream, deformed. Okay, and a variety of shape, size, and thicknesses. Right. So these are some examples of the typical fibers. This is a steel fiber. These are polyethylene fibers. Okay, so various types of fibers are shown here. So the characteristics of commonly used fibers, basically the diameter D, it is between 0.05 to zero point 0.5 millimeter. The length L is basically from 5 to 60 millimeter, and the aspect ratio, that is the L by D value, is around 100. Okay, so these are some of the characteristics of commonly used fibers, right? Then as we know, like mainly the failure of the fibers will occur in tension and due to interface in bond and in concrete, right? So here as you can see, if the fiber, say for example of length L, okay, uh, their half the length is embedded in the concrete or the matrix, okay, and in the other half length, it is pulled by a tensile force T. Okay, and the fiber has a diameter of small d, and it has an bond stress of the matrix is having a bond stress tau acting on the fiber. So what we see is that this one, for it to snap out, the T value, tensile force value, which is sigma into pi d square by 4, should be greater than tau into PDL by 2. Okay, the area of the circumference. So from this, we coined the term of critical aspect ratio. Okay, so that is sigma by 2 tau. Okay, so based on this only we have to design our short fibers. Okay, for short fibers, and how many, what is the volume to be used. Okay, so more is the aspect ratio, more is the tensile force. More is the tensile force given, greater will be the aspect ratio. Also higher will be the this one bond stress, lesser will be the aspect ratio. Okay, so that's why the aspect ratio is mainly dependent, critical aspect ratio is mainly dependent on this one, the bond stress, and as well as the tensile force. Okay, so advantages and disadvantages of using fibers. Since fibers are generally distributed throughout the concrete, many fibers are inefficiently located for resisting tensile stresses, right? And spraying the fibers lead to a two-dimensional random orientation, whereas pre-mixing them during batching leads to a three-dimensional random orientation. Okay, the efficiency factor to take care of the stresses, it depends on fiber length, critical embedment length, and the orientation. Okay, so these are the advantages and disadvantages of using fibers. Okay, the steel fibers, so short discrete lengths of steel with the aspect ratio in the range of 20 to 100. Sometimes they have hooked ends also to improve the pull out resistance. They have high modulus of elasticity because they are steel fibers, right? Basically, they can be classified as per ASTM 8820 into four types. Okay, type 1 is the cold drawn wire fibers, which are manufactured from drawn steel wires. Type 2 is the cut sheet fibers, which are manufactured through laterally shearing the sheets. Type 3 is the melt extracted fibers, which are molten metal which is rapidly frozen into fibers. Type 4 are some other types of fibers. Okay, so this is example of machine fiber. Okay, and they have shown how it is processed and what are its capacity. Okay, what are its parameters and its characteristics. Okay, and based on some PhD work done on it. So the glass fibers, let us come here. So glass fibers are mainly used in non-structural. The steel fibers are used in structural applications, in structural elements, and glass fibers are basically used in non-structural elements. Okay, so the glass fibers, these are conventional glass fibers, which are say borosilicate type. Okay, that is the E glass, soda lime silica type. Okay, which is the A glass. So these are conventional glass fibers such as E glass and A glass. Okay, uh, research has shown that there could be alkali reactivity, okay, which is occurring between the E glass fibers and the cement paste, okay, which impairs the strength of the composite. Okay, alkali resistant glass fibers, air glass, are introduced to address the issue. So research has shown that alkali reactive between e-glass and cement paste, okay, results in strength impairment of the composite, and therefore alkali resistant glass fibers, which are also called as air glass, okay, they are introduced to address this issue. Okay, so the glass fibers, they result in loss in strength and ductility of exterior glass fibers. It has been found, and that is basically because of fiber embrittlement due to the infiltration of calcium hydroxide into fiber bundles. Okay, which results in loss of mechanical properties. Okay, so this reduction of embrittlement, this reduction in mechanical properties due to embrittlement can be decreased to a great extent by using low alkali cement, specially formulated chemical coatings, microsilica slurry for filling the voids in fibers, etc. Okay, synthetic fibers. These are mainly man-made fibers like acrylic, aramid, carbon, nylon, polyester, polyethylene, and polypropylene. Right. So polypropylene, these are the most popular ones and are chemically inert, hydrophobic, and lightweight. They are usually in monofilament form and help in arresting shrinkage and subsidence related cracks. Fibrillation of both polypropylene and polyethylene resins provides better mechanical bonding than conventional monofilaments. They are incompatible with each other and tend to separate. Okay, so during mixing, each fiber conglomerates into a unit with fibrils at its end. Okay, so these are some of the characteristics of polypropylene. Okay, then let us go to acrylic fibers. Okay, so they are used in cement board and roof shingle production. Okay, they exhibit high post cracking toughness and ductility. Right. In case of aramid fibers, they have high tensile strength and tensile modulus. Okay, they are stronger than e-glass and steel fibers. Okay, so these are some of the characteristics. Okay, some of the characteristics of the aramid fibers. Okay, then in case of carbon fibers, okay, so carbon fibers, they are typically produced in strands. Okay, so they are typically produced in strands. They possess high tensile strength and modulus of elasticity, and so these are basically strand produced carbon fibers, and they have high tensile strength, elastic modulus. Okay, in case of wood fibers, so they are processed natural fibers. Okay, wood is basically reduced to a fibrous mass using a process called pulping. Okay, cooking wood chips in a solution of sodium hydroxide, sodium carbonate, and sodium sulfide. Okay, so that gives wood cellulose fibers. Okay, they possess good mechanical properties compared to other synthetic fibers. Okay, so these are some of the criterias basically. So then let us come to properties of different types of fibers. Okay, so as you can see, so these are the various fibers, and the various parameters, okay, they have given here based on literature. Okay, so now let us go into the durability of fibers in concrete. So as we all know, the steel is protected due to from corrosion through a formation of oxidation film on the steel surface, which has a high pH. Okay, this film prevents the steel from coming in direct contact with water and air, and hence steel fibers do not corrode, which is very very obvious and very trivial. Okay, then these are the examples of the various fibers and the coatings. Okay, so as you can see in this A case, okay, the large crack widths in fiber reinforced, both are fiber reinforced concrete examples. Okay, so in case A, you can see large crack widths in fiber reinforced concrete prisms without causing complete collapse. Okay, so cracks have appeared, but the beams have not collapsed. And in the second case B, the fibers on the two faces of a concrete prism, as you can see, here the fibers are popping up, right? So the steel fiber reinforced concrete here, addition of fibers reduces the workability of concrete. Okay, so that is one of its drawback. So for same consistency, cement content, water content, and sand by aggregate. Okay, so all of them need to be increased. Okay, compared to plain concrete. So all of them need to be increased compared to plain concrete for achieving the same amount of consistency. Okay, hamper mixing, transportation, placing, and consolidation. So that has to be kept in mind because it hampers all. The coefficient of variation of compressive strength is similar to that of uh, normal concrete. So the coefficient variation in case of compressive strength is similar basically to that of normal concrete. Compressive and tensile strengths do not change much, okay, with the fiber content. Okay, so that is also one of the parameters. Okay, and flexural and bond strength and toughness of SFRC, they also increase as the fiber content increases. Okay, so this flexural bond strength, toughness, all those things, all those values increase in the case of steel fiber reinforced concrete as the fiber content amount of fiber content increases. Okay, the mix the mix should be cohesive enough, right, to hold the fibers without segregation. The surface area of fibers adds to the total surface area of aggregates. For optimum performance, the quantity of fines required may increase with increasing surface area of the fibers. Okay, the total surface area is directly related to the dosage and inversely related to the size of the fiber. Okay, and total uh, finer material, cement, mineral admixtures, finer portion of fine aggregates, okay, which are typically less than 300 micron sieve, should be at least 400 kg per meter cube. So these are some of the criteria basically which have to be used. Okay, for the mix to be efficient for the fibers, the grading curve, that is the graph of sieve size and percentage passing of aggregates, coarse and fine together. So this that should be polarized towards the finer side in order to increase the carrying capacity. Okay, the combined grading curve of coarse and fine aggregates down up to 75 micron size should be checked for getting smooth grading. It is preferable to use natural fine aggregate. Okay, if it is not available, the available fine aggregate can be modified by combining crushed sand or mixing a small percentage, about 4 to 8% of crusher fines, to improving the continuous grading. Okay, as the number of fibers in a unit volume of concrete increases, the spacing between the fibers reduces. That is obvious. This poses a limit on maximum size of coarse aggregate and its percentage fraction, okay, in the mix, right? The maximum size of aggregate and the proportion of coarse aggregate may suitably be reduced depending on the dosage and diameter of fiber. For keeping the shrinkage low, the OPC content should be restricted while increasing the total cementitious material. Thus, fly ash content can be higher than that permitted in normal concrete. Okay, so these are other factors that needs to be kept in mind. Keep water content to a minimum. Okay, water demand increases linearly with fiber content. Okay, for each fiber percent, an increment of as much as 20 kg per meter cube may be required. Water content shall normally be in the range of 140 to 180 kg per meter cube of concrete, right? To minimize water content, admixtures such as air entraining, water reducing, and high range water reducing admixtures may be used. Typical dosages of superplasticizer, naphthalene, or melamine base are in the range of 0.4 to 1.4% of cementitious content. The proportioning shall also consider the parameters to avoid balling of fibers. So this is one of the main issues with fiber reinforced concrete, which is balling. Okay, so the fibers get accumulated like a ball, and that blocks the very purpose why it is used. Okay, as you can see here, this is the creation of fiber balling. Okay, in SFRs. So the shape, size, and content of steel fibers may be determined considering the required strength and deformation characteristics of the steel fiber reinforced concrete. A steel fiber reinforced concrete should be proportioned, keeping the water content at a minimum while meeting the required performance in terms of workability, etc. High unit water content and sand aggregate ratio could induce bleeding and segregation, okay, and would require hamper, okay, mixing, transportation, placing, and consolidation, okay. So higher water content and sand aggregate ratio results in bleeding and segregation, okay. So that is one of the issues, okay. And if there is lower water content, then that will lead to improper hydration, okay. So that is the other content, other problem, and also it will not give proper workability, okay. So both are the issues, okay. It has to workable also and not result in bleeding segregation also. So considerations for fiber length. So it should be sufficiently long compared to the maximum aggregate size to have the desired effect, okay. So it should be about at least 1.5 times the maximum size of aggregates. It should be about 60 mm, okay, uh, for high reinforcement effect for slabs. Sorry, the length of 30 mm or more is recommended generally. In cases fibers exceed 40 mm in length, special care is needed in such as proportioning, method of mixing, transportation, etc. to ensure that there is no formation of fiber balls without compromising the required reinforcing effect. Okay. If fiber content is between 0.5 to 2%, normal mixing methods may be used, right? The concrete should be thoroughly mixed to get a homogeneous uniform mix. Okay. Increase energy required for this increases energy required for mixing because of the presence of the steel fibers, okay. Up to 2 to 4 times the energy required for normal concrete, okay, may be needed, right? So that uh, that will result in force action. Batch mixture should be used, okay, instead of gravity mixture. And time of mixing should be determined experimentally, right? So all this plays an important role. Fibers should be added to the mixer, ensuring uniform dispersion, okay, and using dispensers or bundled with water soluble adhesive and mixed, okay. So good for flat fibers basically. So all those techniques can be used, okay. When fibers are added in an agitating truck, okay, the concrete should be mixed at high speed, okay. Mixing time for FRC can be 15 to 25% higher compared to concrete without fibers. The variations in the proportions of coarse aggregate in a sample of known size denotes the mixing efficiency in fiber reinforced concrete, okay. For each FRC job, Okay, optimum time for uniform mixing, okay, should be found by trials, and it may change with ingredients, okay, especially such as fibers, okay. Thus it should be checked very frequently basically. So the mixing time will also change with working rpm of the mixture and with wear of the blades, okay, uh, to ensure that the fiber do not form balls, okay. We have to ensure that longer fibers have a greater tendency to wrap around lump and form balls, okay. Chances of balling are higher with higher dosages of fibers, and also higher with higher aspect ratio. So more is the L by D ratio, more will be the this one balling, and also with higher dosage because of volume, increase in volume. So harsh mixes not fluid enough or not workable enough take longer time to mix the fibers without balling, okay. So this one that is one of the uh, this is one of the utility, okay, of using harsh mixes. Otherwise there is a chance of this balling if fibers are added to the mixer first while the other materials aggregate are not enough to keep the fibers away from each other. The balls may form, okay. So all those factors needs to be kept in mind, okay. uh, so if the harsh mix basically if it is not fluid enough, so it takes longer time for mixing, okay, because it is not fluid enough, and that's why without boiling it will also take longer time, and that's why the fibers, okay, uh, also if they are added to the mixture, okay, while the other materials are not enough to keep the fibers away from each other, okay, then also the balls may form. So we have to keep into account everything. So pumping loads are greater than for normal concrete because of the presence of steel fibers, and therefore the piping layout should be appropriately designed, okay. Flexible pipe sections could be particularly vulnerable to abrasion, okay. Therefore keeping the actual placing conditions in mind is vital, and their material diameter, pipe thickness, okay, all should be appropriately selected, okay. Then only it will be useful, okay. So checking the homogeneity of fiber dosage, okay. The content of fiber shall be checked from samples obtained from fresh concrete, okay. Each fresh concrete sample will be placed over a 5 mm sieve and washed with water to remove the fine content. From the remaining mass of aggregates and fibers, the fibers are to be separated manually, dried, and weighed. Okay. The average weight of fibers obtained is used to determine the normal nominal fiber dosage, which shall not be less than 90% of the specified fiber dosage. Okay. For steel fibers, a magnet or an electromagnet can be used to extract the fibers. Okay. The content of fibers can also be estimated in hardened concrete by taking cores and crushing them. Okay. So now let us see the parameters which affect the FRC properties. So concrete is mainly affected by water cement ratio, maximum size of aggregate, sand by aggregate, total aggregate content, etc. Fibers are mainly depend on material. This is steel, glass, shape, size, this aspect ratio, etc. Content, orientation, fiber dispersion, etc. So shape, size, and content of steel fibers are determined according to the required strength and deformation characteristics of SFRC. Steel fibers are either mixed in the mixture with other materials, okay, or are sprayed or added to at the end in the agitator truck. Shape and size, the length ranges between 20 and 60 mm. Diameter ranges between 0.3 and 0.9 mm. And the aspect ratio L to D ranges between 30 and 100. Fiber content ranges between 0.5% and 2.0% by volume, which is equivalent to which is equivalent to 40 to 160 kg per meter cube by weight. Okay, so The steel fibers, okay, they can be sheared fiber, cut wire, machine fiber, melt extraction fiber, etc. Okay, and your the dimensions, they can be basically zero point 0.5 by zero point 0.5 by 25 to 60 flat. Okay, that is a square section, and this is length, so it is basically flat. Okay, and round, that is have zero point 0.5 diameter diameter into 25 by 60 okay, length. So most popular fiber for structural use is the steel fibers, as we discussed, and glass fibers are basically for non-structural use. Okay, so concrete pavement, shotcrete repair, concrete products, etc. These are some of the this one applications. Properties of SFRC. In SFRC, the steel fibers may be assumed to carry tensile stresses only after cracking of the concrete face. Okay, thus the tensile strength of SFRC may be taken to be the cracking or tensile strength of the matrix concrete. Addition of fibers may not lead to substantial increase in the compressive or tensile strength, though the post cracking behavior is a completely different story. Okay, so we have to take that. Whereas the flexural and bond strength and especially toughness of SFRC increase as the fiber content increases, the compressive and tensile strengths do not change considerably with the fiber content. The fibers come into play only after the matrix has cracked. Okay, compressive strength of SFRC is governed basically by the water cement ratio, as in the case of normal concrete. Okay, with the addition of fibers, the workability of concrete gets reduced. For workability in FRC, the sand aggregate ratio may need to be substantially increased as the aspect ratio of the fibers increases. Compressive strength of SFRC is governed basically by the water cement ratio, as in the case of normal concrete. Okay, improve strength in tension, flexure, and shear. Improve crack resistance, ductility, and impact resistance. High crack arresting capability reduces crack width and improves fatigue strength. Okay. High compressive toughness at compressive failure. High flexural toughness in bending, and high resistance. Okay, to impact explosive loads. Okay. Fiber cement bond properties. Characterizing the interfacial bond properties and fiber debonding plays an important role in FRC. Two analytical approaches to interpret the material properties for fiber debonding. Stress brace, basically there are two types criteria. Okay, one is stress brace criterion and one is energy release rate criterion. So in stress based criterion, debonding of the fiber from the matrix, okay, will take place when the maximum shear stress at the interface reaches a critical value. Okay, and in case of energy release rate criterion, debonding will propagate only when the energy flowing into the interface exceeds the specific resistance energy. So these are two criterions to be used. The fiber cement bond properties can be measured by a pull-out test. Okay, fiber cement bond properties. So typical pull-out stress strain plots. So typical tensile behavior are shown for different dosage levels. The load and displacement have a linear relationship. Non-linearity may appear just before the peak load. Okay, a sudden drop of the load is experienced and is followed by a gradual decrease of the load with a displacement representing the fiber pullout from the matrix. Okay, by utilizing the characteristic points on the curve, the interface properties can be estimated. Multiple cracking can be noticed in HPFRC, okay, that is high dosage level, high polymer fiber reinforced concrete. And as you can see here, we will discuss this also now. As you can see here, only one single crack is present. So as you can see, but in the case of this one, HPFR high dosage fiber reinforced concrete, multiple cracks are occurring, as you can see here. Okay, so effect of fiber addition on tensile properties. So in the case of single this one single crack, okay, that is fiber reinforced concrete, they follow the stress strain softening criteria. Okay, so that means we, after reaching the max peak load, the stress with increase in strain, the strength decreases directly. Okay, so incorporation of fibers into concrete improves the tensile behavior, including strength, toughness, and failure mode. Two basic categories: strain softening and strain hardening. Strain softening in the case of low volume fiber fraction, that is not exceeding 1%. Area under a deformation curve is higher in FRC. Usually a specimen is characterized with a single macro crack. Okay, as you can see here, only one crack will occur. So by this the specimen is characterized. In the case of strain hardening behavior, okay, that is the second case where higher dosage level of fiber reinforced concrete is used. So the strain hardening behavior at higher dosage level. So stage 1, elastic behavior of the composite, okay, with few micro cracks. Okay, stage 2, randomly distributed cracks start to localize and form the first major crack. This is known as bend over point BOP, which is denoted by point B. Stage 3, stress carried by fibers is transferred to matrix, okay, through bond, and the matrix cracking occurs when the stresses in matrix exceed the tensile strength of matrix. Stage 4, no further matrix here, basically no further matrix cracking occurs, okay. Load is carried by fibers till they fail in tension, okay. So that is how the stress strain curve behaves, okay. Next, we will see what is the behavior in bending. Okay, the flexural strength and toughness of fiber reinforced concrete are the most important parameters for design and quality control. The flexural behavior of fiber reinforced concrete is evaluated by the enhanced post cracking capacity, which is expressed in terms of a set of toughness parameters obtained from the load deflection curve of the third point loading test according to IRC's SP46 2013. Okay, larger deformation with a reasonably high stress, and hence the area under the stress strain curve is large. Okay, the behavior in bending, the area under the load deflection curve for bending can be used as an index to estimate the energy absorbing capacity or toughness of the material. Increased toughness means improved performance in resisting fatigue, impact, and impulse loading. Improved toughness also leads to a better ductility. So that is the use of using fiber reinforced concrete. So to characterize the toughness of fiber reinforced concrete beam specimens under bending, the concept of toughness index has been proposed. Okay, the toughness index utilizes a ratio of the area under the load deflection curve of an FRC beam up to a specified deflection value to the area up to the first crack, or simply an area up to a specified deflection value. Okay, different standards define the toughness index differently. So as per ACI, toughness index is equal to area of OABEG. Okay, that is up to 1.9 mm deflection by the area up to the first crack. Okay, that is OAJ. Okay, or it can also be defined as area of OABF. Okay, divided by area of OAKL. Okay, so that is the normal concrete. Okay, area of normal concrete, area of the fiber reinforced concrete by area of normal concrete. So both can be done. In the case of Japan Concrete Institute, according to them, so toughness is measured by the area under curve till L by 150 deflection. Okay, that is span by 150. So various criteria can be used, and based on compressive tensile flexural strength, okay, various deformation parameters have been defined, such as total toughness, as you can see here, E, toughness ratio, that is total toughness E by P max into delta naught. Okay, uh, equivalence flexural strength, okay, which is equal to E prime, okay, by delta naught. Okay, and residual flexural strength ratio, okay, which is equal to P naught, okay, by P max. Okay, so these are some of the ways, okay, these are some of the ways through which we can find out the flexural and all those toughness ratios. Okay, so as you can see, toughness of SFRC, this has been done in research. Okay, research have been performed on this with different type of fibers and fiber content. Toughness of SFRC changes a lot. Okay, at different volumes of fiber. So with the increase in deflection and load, okay, as you can see, with the increase in fiber volume, the strain softening, okay, it's reduced. Okay, and strain hardening occurs, and also with using of various fibers. Some are showing strain softening, whereas some are not. Okay, so these are the criteria and these are the differences. So as you can see, if you compare a plain beam and a SFRC beam, okay, so SFRC beam has a higher shear capacity compared to plain concrete because of the fibers, and RC beams do not fail by shear. This we will not see here in this case. When shear, even when shear reinforcement are not used because of the fibers, okay, they increase the tensile shear flexural capacity and also the toughness. Okay, now maximum moment of RC beams without shear reinforcement, if you see, okay, so the two above two cases of reinforced concrete, fiber reinforced concrete, so one is cut wire and one is sheared. Okay, so both are having higher moment as compared to the plain concrete. Okay, and you can see that here in the plain concrete, in the when the A by D ratio, that is the shear span by depth ratio, is 2.5. Okay, so there is large reduction of moment, but that is not found in the fiber reinforced concrete. Although in shear some reduction is found around 2, but that is not that high as compared to this one. This is not that high as compared to this one. Okay, and that is also maybe due to some initial reasons. Okay, initial some either some experiment problem or some the initial experiment problem or some defects. Okay, otherwise it is largely constant. And if you see the design of flexural members with SFRC, okay, so you will see that as compared to plain concrete, SFRC beam has higher tensile capacity compared to plain concrete. Tensile stresses in SFRC in the tension zone can be considered. Okay, so we can take the tension zone and consider the tensile capacity. Okay, so properties of FRC, therefore, we can say that improve strength in tension, flexure and shear, improve crack resistance, ductility and impact resistance, improve high crack arresting capability, which reduces crack width and improves fatigue strength, high compressive toughness at compressive failure, high flexural toughness in bending, and high resistance to impact explosive loads. Okay. Applications of FRC, they can be applied to pavements and tunnel lining with reduced thickness. Tunnel lining in case of concrete without reinforcing bars by increasing the fiber content. Increase the concrete's resistance to freezing and thawing, okay, thereby increasing its durability, and increase the shear capacity of members. Okay, now shortcreting. Okay, so how can we use this one fibers in shortcrete also. So short fibers are more workable but less effective in reinforcing concrete. Short fibers of 20 mm or less permit easy spraying and are ideal for applications such as shortcrete. Nominal length and aspect ratio of steel fibers to be between 20 and 60 and between 30 and 80 respectively. Okay, so with this we come to the end of this week's course content. Now let us go to the solve problems. Okay, so first question, first question, in the context of rheology, consider the following statements. Statement 1, rheological behavior of fresh concrete affects the ways it can be processed and placed, which is true as we discussed initially. Statement 2, rheology is the study of flow behavior of materials exhibiting a time dependent response to stress. Okay, so that is also true. Okay, so that the response is basically in terms of your shear stress and your shear strain rate. Okay, so which is obtained by torque and viscosity. Okay, so both are true, so both statements are true. The first option is correct. So yeah, first option is correct. Second question, basically it is that in the context of rheology, consider the following statements. Statement 1, behaviors in fresh concretes can be obtained from direct measurements of torque and flow rate. Okay, and in rheometers, using rheometers, so that is basically correct. Okay, so flow behavior mainly allows gives direct measurement of torque and flow rate. Okay, and secondly, viscosity, which is representative parameter for assessing the flow is defined as a ratio of stress to strain. So second statement is not correct because viscosity, okay, that is basically the ratio of stress to strain rate, not only strain. Okay, so the second option is incorrect. So statement 1 is true and 2 is false. So second option will be correct. So yeah, second option is correct. Third question, in the context of self compaction ability of concrete, consider the following statements. Okay, statement 1, to increase the deformability of the paste, increased powder water ratio and use of superplasticizer and adopted strategies. Statement 2, to adjust the viscosity of paste, water powder ratio and use of viscosity agent are adopted strategies. Okay, choose the best alternative among the following. So first statement is wrong because increasing deformability will result in increasing water powder ratio or decreasing powder water ratio. Okay, so this is wrong. And second, adjusting viscosity. Okay, water powder ratio can be tweaked, and use of viscosity agent can be also helpful. So one is false and two is true. So third option is correct. So as you can see, one is false and two is true. Okay. Fourth question, in the context of suspensions, consider the following statements. Statement 1, suspensions can be defined as solid particles dispersed or flocculated in liquids. Statement 2, factors such as volume of solid particles and degree of agglomeration affects the flow behavior of suspensions. Choose the best alternative among the following. Okay, so suspensions can be defined as solid particles dispersed or flocculated in liquids, so that is true. And factors such as solid particle volume, degree of agglomeration, they affect the flow behavior of suspension. Now, that is also true. So both the statements are true. Therefore, the first option is correct. Okay. So both the statements are true. Fifth question, in the context of flow behaviors of concrete, consider the following statements. Statement 1, increasing the water to cement ratio lowers the yield stress and uh, plastic viscosity of concrete. Okay. And statement 2, increase in total aggregate content TAC results in decreased plastic viscosity of concrete. Choose the best alternative among the following. So, first statement is true. That is, increasing water cement ratio will definitely lower the yield stress and plastic viscosity in concrete. And second statement is false because increasing total aggregate content, okay, that will increase the plastic viscosity, okay, not decrease. So one is true and two is false. That is, second option is correct. So yeah, second option is correct. Sixth question, consider the following deficiencies in cement-based composites. 1, relatively low tensile strength. 2, low flexural performance. 3, shrinkage cracking. 4, low energy consumption capacity. Which of the deficiencies mentioned can be improved by adding fibers to the cement-based composites? So yeah, so fiber reinforced concrete can help in increasing relative tensile strength. Okay, uh, then increase the flexural performance. Okay, reduce the shrinkage cracking and also increase the energy consumption capacity or toughness. Okay, so all the four options are all the four criteria can be improved by adding fibers to cement based composites. Therefore the fourth option is correct. As you can see, the fourth option is correct. Seventh question, in the context of using fiber reinforcement versus conventional reinforcement in concrete, consider the following statements. Statement 1, presence of fibers modifies the properties of concrete per se, but conventional reinforcement does not affect the properties of concrete. Statement 2, fibers in the cement matrix are randomly distributed, whereas reinforcing bars are at predetermined locations. Okay, so choose the best alternative among the following. Okay, so yeah, so as you can see, the first option is correct. Okay, because presence of fibers modifies the properties of concrete uh, as requirement as required per se, but conventional reinforcement does not much affect the properties of concrete. Okay, so that is true. First option is correct. And the second statement, that is, fibers in the cement matrix are randomly distributed, whereas reinforcing bars are at predetermined location. That is also true. Okay, so both the options are correct. So first option, that is both the statements are true, is correct. So as you can see, both the statements are true. Eighth question, in the context of fiber volume ratio in fiber reinforced composites FRCs, consider the following statements. At lower fiber volumes, tensile strength of cement composite is greatly enhanced. And second statement, at higher fiber volumes, toughness of cement composite is primarily enhanced. Choose the best alternative, okay, among the following. Okay, so as you can see here, okay, So in the first statement, okay, in the first statement at lower fiber volume, okay, the tensile strength is not enhanced. In fact, it is the toughness, okay, which is enhanced. So first option is wrong, okay. And at high fire volumes, okay, tensile strength is enhanced, not toughness. So second is also wrong. Okay, so 1 and 2 both are wrong. So both the statements are false. That is, the fourth option is correct. So as you can see, fourth option is correct. Ninth question. In the context of classifying fiber reinforced composites FRCs based on fiber volume, which of these are correctly paired? Low fiber composites improve mechanical properties. Moderate fiber composites reduce shrinkage cracking. High performance fiber composites improve strain hardening behavior. Okay. So as you can see, low fiber composites results in reduced shrinkage cracking. So first option is wrong. Second, if you see moderate fiber composites, that will exhibit improved mechanical properties. So that is also wrong. But third, if you see high performance fiber composites, so that results in improved strain hardening behavior at content more than 5%. So third is correct. So only three, that is third option is correct. So as you can see, only three. And let us come to the last question. In the context of fiber reinforced composites, FRCs, consider the following statements. Statement 1, aspect ratio of fibers used in matrix is chosen considering the maximum tensile and bond stresses. Statement 2, method of mixing fibers in matrix plays critical role in fibers orientation in matrix. Okay, choose the best alternative among the following. So aspect ratio of fibers, okay, used in matrix, that is chosen considering the maximum tensile and bond stress using that parameter L by D is CR equal to sigma by 2 pi. So 2 tau, sorry. So one is true. And the method of mixing, okay, fibers is in matrix plays critical role in fibers orientation in matrix because of the fear of balling. Okay, so proper water ratio should be maintained. It should not be less for unworkable and more time taking, and also not be more for bleeding and segregation. So both are true. Okay, that's why method of mixing fibers plays a critical role along with water cement ratios. Okay, because of the balling phenomenon. So both are true. So both the statements are true. First option is correct. So as you can see, both the statements are true and the first option is correct. Okay, so yeah, so with this we come to the end of today's discussion. Okay, we learned about rheology, its effect, okay, how the flow parameters and the fresh concrete parameters are affected based on rheology, okay, and why it is important. And second, we studied a special concrete which is fiber reinforced concrete and its applicability criteria and its utility, okay, and also its some of its drawbacks which can be overcome by adjusting the parameters. Okay, so with this we come to the end of today's class. If you have some questions you can ask. Okay, so with this we will end today's meeting. Okay, so I am signing off. Bye.